Parametric equations, part 2, eliminating the parameter. So many parametric equations have graphs that can also be represented by rectangular equations, as we've already seen. So the process of converting from parametric to rectangular is known as eliminating the parameter. So let's say that we had this set of parametric equations, x equals t squared minus 4 and y equals 1/2 t. Well, to solve, what you could do, and there's more than one technique, but this is a pretty good technique, is you want to solve for one of your equations for t and substitute into the other one. So I'm going to choose this bottom equation for y, because it's easier to solve for t there. So I just have t equals 2 times y, and then I'm going to substitute for t into the other equation. So now I'm going to have x equals 2y squared minus 4, and that becomes x equals 4y squared minus 4. And that's it. That's the rectangular equation. Now, you may recognize that x equals 4y squared minus 4 would be the equation of a sideways opening parabola. It's not written in standard form of any kind, but we do see that the y is squared and the x is not, and so that's going to mean that it's not going to be a function, and in fact, it will be a sideways parabola. So sometimes you have to alter the domain of the rectangular equation to make sure that the graph matches it for the parametric equations. And let's have a look at example 3. So we want to identify the curve represented by these equations, which basically means that we need to take these equations, these parametric equations, and convert them over to rectangular. We're going to solve one of these equations for t. I'm going to choose this equation. It's going to be easier because there's only one t in it, whereas the y equation we have 2 t's, and it would be harder to solve for t. So I'm going to first square both sides. So I have x squared equals 1 over t plus 1. I'm going to cross multiply, essentially. That's x squared times t plus 1 equals 1. And then I'm going to divide by the x squared. So I have t plus 1 equals 1 over x squared. And then subtract the 1. So I have t equals 1 over x squared minus 1. Now I'm going to substitute that for the t in the y equation. So now we have y equals 1 over x squared minus 1 over 1 over x squared minus 1 plus 1. And look at that, we have a beautiful complex fraction. Luckily in the denominator, the negative 1 plus 1, that becomes 0, so I now have 1 over x squared minus 1 over 1 over x squared. Now, one of the fastest ways to simplify a complex fraction is to multiply the top and the bottom by the common denominator. Well, they both have a denominator of x squared, so I'm going to multiply the top and the bottom by x squared. So now I'm going to have, after I distribute there, 1 minus x squared over 1, or in other words, 1 minus x squared, and that's equal to y. So it seems that this would be our rectangular equation to match these parametric equations. However, we need to make sure that we include any domain restrictions. So if we look at our equation as given, we can see, for example, we have a t in the denominator for the y. We know that the denominator cannot be 0, so that means that t cannot be equal to negative 1. But even more importantly, we can't have a negative underneath this radical for this equation here. I know that the t plus 1 must be greater than 0. So that means that t must be greater than negative 1. Well, how does that correspond to the x? Well, if you think about it, if your t, anytime that your t is greater than 1, your x is actually going to be greater than 0. So for our answer over here, we're going to say where x is greater than 0. So our rectangular equation is y equals 1 minus x squared, where x is greater than 0. So the graph of this rectangular equation here with this restriction on x will result in the same graph as these parametric equations. And of course, you can test that in your calculator. Let me explain one more time why the x has to be greater than 0, because that can be confusing for students. When you're looking at your restrictions on your original parametric equations, you see here that the t cannot be equal to negative 1 for the y, but actually more importantly, the t has to be greater than negative 1 for the x. And that sort of overrules the t cannot be equal to negative 1 on the y. So we're really concerned about what's happening with the x. The t has to be greater than or equal to negative 1 in order for this expression to work. And when that's true, when t is greater than negative 1, then the x is always going to end up being a positive number. So in other words, x is always going to end up being greater than 0. Let's take a look at example 4. All right, this one is quite different than anything that we have seen before. We have now trig. So x equals cosine of t and y equals the sine of t. And we want to describe the motion of the point. That usually means what's the orientation of the point. And so when we're trying to change from the parametric over to rectangular, we said before that we want to like isolate the t and substitute, but that would be pretty ugly here. So I'm going to do something a bit wild here. I'm going to try a different strategy. I'm going to take these equations, x equals cosine of t and y equals the sine of t, and I'm going to square both equations. So now I'm going to have x squared equals cosine squared of t and y squared equals sine squared of t. So this is a totally different strategy that's often used whenever you have trig. And here's another part of this strategy. We are going to add these equations. That's right, folks. We're going to add these equations. So on the left-hand side, I'm going to have x squared plus y squared. And on the right-hand side, I'm going to have cosine squared of t plus sine squared of t. Uh-oh, this should start sounding familiar to you. You remember there is a Pythagorean identity that we've studied before. That's cosine squared of theta plus sine squared of theta is equal to, you guessed it, 1. So cosine squared of t plus sine squared of t is equal to 1. And there it is. That's our equation in rectangular form. Oh my goodness. And you know what that is? That is the equation of a circle whose center is at the origin and whose radius is equal to 1. That's wild. Let's graph this circle and check it out and determine the orientation. So to graph it, of course, I'm going to make my 3 columns for t and x and y. For t, I can choose anything that I want, and since my equations were trig equations, I'm going to sort of go around the unicircle. So I'm going to have 0, pi over 2, pi. So I'm going to go back up here to my parametric equations, and I'm going to let t equal to 0, and I'm going to find my x and my y. So when t is equal to 0, I'm looking at cosine of 0, which is 1. And let's go ahead and do the sine. Sine of 0 is 0. When t is pi over 2, the cosine is 0 and the sine is 1, and so on and so forth. So those are my values for x and y. Again, plugging in the values that I chose for t into my parametric equations. So now I'm going to set up my axes and graph. Here are my axes, my x-axis, my y-axis, and I'm just going to plot these points. So first I start at 1, 0, then 0, 1, then -1, 0, then 0, -1, and then back to 1, 0. Holy smokes, guys. That's basically the equation for the unit circle. And did you see how my shape just automatically turned into a circle? That was pretty cool. And there's the graph of the set of parametric equations. And the motion or the orientation is indicated with the little arrows. Let's take a look at example 5. So like in this other example, the previous example, we have some trig involved here. So 2 cosine of t plus 4, and then y is 3 sine of t minus 1. We're going to eliminate the parameter and then graph the resulting rectangular curve. So whenever you see these things with a trig, you're going to want to be thinking in terms of, cosine squared theta plus sine squared theta is equal to 1, that Pythagorean identity. And sometimes it's sister identities, like the secant, one was the secant, the tangent, and so on would be used as well. So let's write down my equations I'm given. So I have x equals 2 cosine of t plus 4. You have to be careful to not make it look like you're saying cost. 3 sine of t minus 1. So what I could do here is one of two things. I could either go ahead and square both sides, or I can isolate the cosine and then square both sides. So I'm going to choose to do that. I'm going to isolate the cosine. So I'm going to have x minus 4 equals 2 cosine of t, and then divide by 2. So x minus 4 divided by 2 is cosine of t. So now when I square both sides, and watch this, I'm not actually going to expand it. I'm just going to write x minus 4 over 2 squared is equal to cosine squared of t. Or better, I can call that x minus 4 squared over 4 equals cosine squared of t. Let's do the same thing over here. So I'm going to isolate the sine. So I'm going to have y plus 1 equals 3 sine of t. Y plus 1 divided by 3 equals sine of t. Now I'm going to square both sides in an effort to get it similar to that Pythagorean identity. So that's y plus 1 over 3 squared equals sine squared of t, or better, y plus 1 squared over 9 is equal to sine squared of t. So now, again, what we can do is we can add these equations. So if I were to say, let me rewrite them. I'm going to have x minus 4 squared over 4 equals cosine squared of t, and y plus 1 squared over 9 is equal to sine squared of t. And now, folks, if I add these two equations, this is wild. This is really wild. We're going to have x minus 4, so minus sign, squared over 4 plus y plus 1 squared over 9 is equal to cosine squared of t plus sine squared of t. We know cosine squared of t plus sine squared of t is equal to 1. I have x minus 4 squared over 4 plus y plus 1 squared over 9 is equal to 1. Folks, do you know what that is? You know what that is. That, ladies and gentlemen, is the equation of an ellipse. That's right. And we are about to graph it. We know that the center of this ellipse, we're not actually going to graph it the way that we normally graph ellipse. We're going to graph it from the parametric form. The center of that ellipse is going to be a 4, -1, and so on. I'm going to rewrite the equations that I have from earlier, the given parametric equations. Okay, so I have rewritten the equations that I was given. So I'm going to set up my table with t and x and y. And then for my values of t, again, because of the trig, I'm just going to go through the whole, the unit circle. So we're going to start with 0, pi over 2, and I'm going to plug these values of t into each of the equations. So I'm going to do the x ones first. So if I plug 0 in for t, so I'm going to have x equals 2 times the cosine of 0 plus 4. Cosine of 0 is 1, so x equals 2 times 1 plus 4, so x equals 6. So we're going to have 6 here, and I'm going to do the same process for the rest of those angles. And then I'm going to do the same process for the y's. All right, so there's my table of values. Now I'm going to set up some axes and graph. Set up my axes. This is my x-axis, this is my y-axis, and I'm going to plot these points in order. So first, 6, -1. So we kind of have, it looks kind of like a circle on my paper here, but it's just because my scale is off. It is a vertical ellipse with the direction, like, or the orientation going like so. There it is, ladies and gentlemen. We have given some parametric equations. We eliminated the parameter. We saw that it was the equation of an ellipse. And then we graphed the resulting rectangular curve. We had to do it from the parametric form so that we can determine the orientation. So let's have a look at example 6. So these are actually pretty easy because they have to give you the parameter. They're giving you a rectangular equation. So it's sort of like we're going backwards of what we were just doing. We have the rectangular equation and we want to turn it into a parametric equation, but you're given this particular parameter. If you have t equals 1 minus x, it's pretty simple just to solve this equation for x. I'm going to add the x to the side, so I have x plus t equals 1, and then subtract the t, so x equals 1 minus t. That would be 1/2 of my set of parametric equations for the x. And then for the y, I'm just going to substitute this into my rectangular equation there. So I'm going to have y equals 1 minus t squared. So just substituting 1 minus t for the x. And now I'm going to expand that. So y equals 1 minus 2t plus t squared. So that is 1 minus 1 plus 2t minus t squared. And so that just becomes 2t minus t squared. And so that would be the other half of my parametric equations for the y. And that would be converting from rectangular to parametric. And you could graph this rectangular equation. It's just a parabola that opens down, and compare it to the graph of these parametric equations and see that you get the same thing.